Hello everyone. Today we're going to start on 1.2, which we're going to try to give some kind of geometrical interpretation of what is a vector. So we actually kind of started that last section 1.1 where I told you that when we have a vector, we can actually consider it to be a position vector, which basically allow us to define a position in space. So today we're going to talk about some more geometrical interpretation of what's happening with a vectors or position vector, but also talk about some of the vector operation that we define on vectors and how can we interpret them geometrically. So consider the following. Let's say we're given two position vectors. Let's say vector x and vector y. The first question we try to answer is, what does it mean geometrically? So algebraically, we know how to add two vectors together. We just basically add the corresponding numbers together. But does it have a geometrical interpretation when we do that? When we add or subtract, which basically means add the opposite in technically, these two vectors. What happens when we add or subtract these two vectors? What does it mean? So let's talk about what happens when we're adding. When adding two vectors, what we're going to do is we have to follow what we call the parallelogram rule. So what is the parallelogram rule? Well, basically we mean this. So we let's say we have these two vectors, vector x, and let's say we have a second vector, vector y. So what happened when I try to add these two vectors together? What we're going to do is to basically use these two vectors as two adjacent sides of a parallelogram and kind of form a parallelogram out of these two vectors. So this vectors here is kind of parallel to the x, and this one right here is kind of parallel to the y. And when you form this parallelogram, the position vector that defined from here to here become the vector x plus y. Now, interesting thing to note is the following. In this interpretation, notice that if we use vector x, if vector x and vector y are both position vector, then what must be true is that the sum x plus y is also a position vector. Reason because it also originates at the same one point, and that same one point would be the origin. So if vector x is a position vector, that means this has to be origin. It points to a position right here. And then vector y must start at the origin right here, point to a position right here. And then the sum would actually be another position vector that point to a different location, somewhere between the two. And if you think about it, you can easily draw a picture to kind of illustrate. Suppose we have the following. Let's say vector x is the vector 2, 1. And let's say vector y is the vector negative 3, 2. Then the question is, can we find vector x plus vector y? And let's draw a graph and just see how it looks like. Okay? So, what is vector x plus vector y? Well, guess what? It's very easy. You just simply add the two vectors together. So it's 2, 1 plus negative 3, 2, and therefore come out to be negative 1, 3. Graphically, what happened? Well, let's see. So it's kind of hard to draw on using this, so bear with me if my graph doesn't look nice. So let's assume we are doing our two vectors. So vector x is 2, 1. So maybe I'll do this. Let's say 1, 2, and 1, 2, 3, and then I guess I can do 1, 2. That's good enough. Okay, so vector x will be the vector 2, 1. So this is my vector x 2, 1. It identified the point 2, 1 on the graph. And remember here, because when we use the position vector, we kind of also interpret it as a coordinate vector using a standard basis. And because we're using a standard basis, the coordinate vector and the position vector are exactly the same. Therefore, that's the reason why the coordinate for the endpoint of this position vector is also 2, 1. And as we discussed, if we are not using a standard basis, then the position vector could be different. Negative 3, 2 will be this one. Let's see if I can do that. Okay, so there you go. Okay, it's kind of bent, but that's okay. There's vector y, which is negative 3, 2. So if I were to draw myself a parallelogram, so let's see if I use a different color, then what I have will probably be something like this. Maybe I did this. And then it formed the sum right here. Okay, let's see if I can do better. Maybe I go this way. A little bit. Alright, let's try this again. Alright, there you go. Kind of better. And that will be my vector x plus vector y, which will be the vector negative 1, 3. Okay, on your test, you will be asked to draw me a graph that illustrates addition between two vectors. And what I would like to see would be the following. Number one, you have to draw generically what sum of two vectors look like. So that basically I'm asking you to draw is this picture right here. Now, very important when you draw that picture. So these are things that you want to write down, because I'm telling you what I'm expecting you to do on your test. And if you don't listen to what my expectation is, then when I grade it, I'm going to have to take off points. So don't force me to do that. The general idea is that you have vector x, you have vector y, then the sum will have to be in between them. But the problem is the following. If you simply draw the sum in between the two, there's really no way you draw it correctly, because it's not anywhere between the two. It's this specific vector between the two that form the diagonal of the parallelogram. So in order for you to correctly show me this picture, you have to kind of draw me the parallelogram and then draw the diagonal as the sum of the two vectors. Every year, no matter how many times I said this, some students will draw me these two vector x and y and then draw me a line between without explicitly showing the parallelogram. And without showing the parallelogram, I do not know, you understand, what the sum of the two vectors should be. It's not just a random vector in between x and y. It's not. It's a specific vector between x and y that satisfies the parallelogram rule. Okay? So please make sure you do that correctly. And also one thing that you do not want to do is to draw axes. Okay, this picture is specifically showing you how to add two vectors in R2. This picture is a generalized picture showing you how to add two vectors in any dimension. That's what you would be asked to do on your next test. Don't draw this. Draw this. All right? So next, what would happen if I subtract two vectors together? So, well, when you subtract two vectors together, it's very interesting, because there are basically two ways to interpret it. Oh, sorry. All right, there you go. There are basically two ways to interpret what happened when you subtract two vectors together. So really depending on how you want to interpret it. So let's say given vector x and vector y, what does vector x minus vector y represent geometrically? So the most basic interpretation is this one. So if I have vector x minus vector y, I can say, well, that's the same thing as vector x plus negative y. So what does that mean? Well, that means that we're basically doing a vector addition, but we're actually defining not adding x and y together, but adding x and opposite of y together. So, vector negative vector y is basically the opposite of vector y. So how does it work? So, well, let's consider we have vector x, and let's say here's my vector y. So if I want to add x to negative vector y, the first thing I have to do is to define negative x. Negative y, I'm sorry. Negative y, which is basically the opposite of y. So basically it's the opposite rate. So if you draw it correctly, negative y and y should form a line. But negative y also have to have the same length of positive y, but just go in the opposite direction. And we'll talk about how to define length in a little bit. And then now I can then add these two vectors together, and the way to do that would be to, well, form parallelogram. And then here, this vector become x plus negative y. All right. Now, important to notice that what if we want y minus x? Well, when we do y minus x, excuse me, when we do y minus x, you basically reverse the order of which you subtract, and therefore, basically meaning that in this case, you're actually adding y to negative x. And therefore, in that case, you actually have to draw negative x, so here's x. You have to draw negative x, which probably go this way, and then you'll combine that with y. And what you form will actually be the same as x plus negative y, but in the opposite direction. Which kind of makes sense. Because that's what happens with real numbers. When you subtract backward, you get the same number, but just opposite of it. Now, I did say that you could interpret two different ways. This is probably a good way to interpret it, using vector addition and add negative y. And it makes sense because we define what we call vector addition, and we did not define what we call vector subtraction. Okay? But we can actually try to interpret it as a subtraction, and when we interpret it as a subtraction, it actually has a different meaning to it. Okay? Before I do that, I want to write this down. So note the following. Vector x minus y is actually equal to negative of y minus x. So that's what we will talk about. If you do y minus x, it will actually form the vector on this side, opposite to this one. Okay? So what happens is, if you do want to think of a subtraction between two vectors, what will happen? So imagine that we have these two vectors, vector x minus vector y. So graphically, we have these two vectors, vector x right here, vector y right here. Then geometrically, what does it mean when I subtract from these two vectors? Well, what we get would actually be referred to as a direction vector. Now, I will show you why this is called direction vector. So direction vector. So what is the direction vector? Well, direction vector is actually this. So remember, in a parallelogram, there are two diagonals. So one of the diagonal, which is this one, kind of go this way, will represent the sum between x and y. So it shouldn't be surprising to you that the subtraction between two vectors would actually form what we call the difference, would be the other diagonal. But however, here's the interesting thing. X minus y is a direction vector. One key thing about direction vector versus position vector is a position vector, the beginning of the position vector must be on the origin, while direction vector simply try to indicate direction between two positions. So in this case, this direction vector actually become this. X minus y become the direction vector that go from the end of y to the end of x. And that's called x minus y. And interesting thing enough, if you draw the same exact vector but go backward from x to y, that is called the direction vector y minus x. What is a direction vector? So worth writing down for yourself. A direction vector can start at any point, and it's meant to show the direction and the distance between any 2 points in space. And if you think about that definition, you can also consider position vector a direction vector that show a direction from the origin to any point in space, which is the correct interpretation. Okay. Now, interesting thing to note is the following, is that this direction vector, this one and this one, they are actually identical except that one is opposite direction to the other. It would not make sense that for them to have different length because it's basically distance between 2 points. And so, therefore, one of the useful ways to use direction vector is to actually use it to calculate distance between any 2 points by showing the length of the position vector of the direction vector between the 2 points. So then the next logical question would be, well, how do you find length? So to find length, you actually know how to do that already, because you learn how to find you learn a Pythagorean theorem already. But the problem is that Pythagorean theorem only allow you to actually calculate length of just vectors in R2. What we're going to talk about would be a generic formula to calculate the length of a vector in any dimension. So let's say we're given a vector in Rn, and let's call this vector x. So vector x is equal to x1, x2, dot 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 to xn. I'll get used to seeing this expression right here. We're going to do that a lot because a lot of things that we define would have to define generically on any dimension. So I'm almost always start with something just like this. What is the length of vector x? The length of vector x is given by the formula right here. So the notation for length is actually a notation that you learned before. It's the absolute value symbol. But when you use that on a vector, it does not, I repeat, it does not represent absolute value. There's no such thing as absolute value of a vector. Okay, absolute value is a operation on only real numbers. So the reason why we use the exact symbol seems like that should be confusing, and it is. But the reason why we use the same symbol because the absolute value of a real number is technically the length of a vectors in R1. So that's the reason why the notation being used here is actually more the notation being used for length first, and then someone realized, oh well, the length in R1 have the same effect of making everything positive, and let's just call that absolute value, and therefore we use a notation. So the length of vector x is given by this formula: square root x sub 1 square plus x sub 2 square plus dot 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 plus x sub n square. And so this is basically the Pythagorean theorem generalized to nth dimension. Okay? So if you look at it, if you just simply cover up the rest of the formula and just do the first two, that is basically what the Pythagorean theorem looked like. And this just allowed me to extend it to higher dimension. And so therefore, one way to use this length is to basically calculate distance. So once again, let's say here we have the origin, and let's say here 2 points, let's say point A and point B. Then what happens is to find the distance between them. Let's say we try to calculate this distance right here between these 2 points. Then what we go basically do is to define, oops, I missed. All right, let's try this again. It defined this vector, let's say I'm going to call vector A, and this vector, which is called vector B, and then define the direction vector between them, which you can define it to be A minus B or B minus A, depending on which way you want to do it. The vector that I read right here would be A minus B. Oops. Or you can do this vector. Oops. Okay. Which is b minus a. And then the distance would just simply become the length of these two things, and you can now use the length to calculate, use this formula to calculate the length. Now, I'll show you a very simple example to kind of illustrate how to use the length formula. Suppose I ask you to, let's say I want to say, let vector x equal to the vector 1, 2, 0, negative 5, 3. And I'm going to ask you to go ahead and try to find the length of vector x. So then what you go do is just simply use the formula. The length of vector x basically tell you to do the following. Take the square root, and they'll basically take each of these numbers and just square them and add them up. So become 1 square plus 2 square plus 0 square plus negative 5 square plus 3 square. Notice, please put a parentheses around negative 5, then put the square. Otherwise, you get a negative number here, which would mess up the entire math. And if you do it correctly, that becomes radical 39. So that will be the length between, that will be the length of vector x. Now, be very interesting to notice the following, is that the length of a vector is actually come out to be a single scalar. And it makes sense because it's a length value. A length value doesn't have a direction, but simply have just a magnitude. And the magnitude should be represented by a single number, which in this case, radical 39. And when you have multiple numbers represented together as in a vector, then that means you are also defining a direction. Okay, so different thing. Length is no direction. Okay. Now, since I already mentioned to you, you could actually find the distance between two position vector by forming the difference between them and then take the length. We can definitely try that. So here we go. Let's say I ask you to find the distance between these two position vector, vector A, which is 1, 3, negative 2, and let's say vector B, which is 0, negative 1, 5. And so how do you find the distance between them? So please, the first, remember, don't do this. Don't find the length of A and don't find the length of B and then subtract them, because that's not mathematically how you find the distance. You basically find out what's the distance between this length and this length, which would not equal to the distance between them for the most part. You might get lucky and happen to be the same length, but I highly doubt that would be the case. So how do you find the distance between them? So what you have to do is the following. So realize that the distance between these 2 points is actually equal to the length of vector A minus vector B, which basically using this arrow pointing from B to A, or the length of vector B minus vector A. So how do you calculate this? So I'm just going to do vector A minus vector B. So I'm going to say this. I'm going to just say find the length of 1, 3, negative 2 minus 0, negative 1, 5. So basically what we're doing is a vector subtraction, or technically vector addition of the opposite vector first. And then once we do that, then we can actually form the length. So that equal to absolute value or length of, when I do 1, 3, negative 2 minus 0, negative 1, 5, I get 1 minus 0, which is 1. 3 minus negative 1 is 4. Negative 2 minus 5 is negative 7. So this right here, in between the two absolute value line, this vector 1, 4, negative 7 is the direction vector that go from B to A. Meaning that if you take the position vector B and you add this direction vector to it, it will give you position vector A. Okay? And now I can try to find the length of this thing. So that would be absolute radical 1 square plus 4 square plus negative 7 square. And if you do your math correctly, that comes out to be 66. There you go. All right. So one very interesting thing that I could ask you to do, which you likely to run into in homework problem, homework assignment, as well as you might run into on the test, is something like this. And I will let you do the problem, and then we can talk about the answers. So given that the vertice of a triangle are defined by the following position vector. Let's say vector x is 1, 2, 3. Vector y is 2, 0, negative 1. And vector z, which is equal to negative 1, 5, 2. Find the length of each side. And I'll let you do this problem on your own, and then we can probably go over it during class. But something I do want to point out that's interesting is the following. Notice that I did not say the vertices of a triangle are defined by the following coordinates. Why not? Well, the problem is that if I do say coordinates, then I must also talk about what is the basis. That means I have to write down a following coordinate using the standard basis. And if I use a different basis, that will actually screw up the math involved. And the reason why I screw up the math involved because then the coordinate doesn't truly define where the position is unless you also work on it with the basis. So therefore, you see us in this class define position in space, not using coordinate vector, but more likely using position vector, which is universal, compared to position coordinate vector, which is relative to the basis. And we don't want to have the extra math involved that we have to deal with basis at all. So that's the reason why we'll mostly define everything using position vector. Now, what does that mean for all of you? Well, for all of you, that just simply means that you can just treat the position vector as the coordinate vector that you normally been using, because for the past 11 years or 10 years that you're learning math, you have been using basic coordinates so far. And for the most part, you can assume when a basis is not given that you are using the standard basis, unless somewhere in the question indicate otherwise. But if there's no indication of what basis you're using, you can assume you are using the default standard basis. Okay? So I'm going to leave this problem to you. You can definitely try to do the problem and then compare your answer with your classmate. However, important to understand is and pay attention to is the following. These are position vectors that define where the vertex is. These are not the vector that define the side of the triangle, which is what you're looking for, which the length of those are what you're looking for. So hopefully you catch what I'm trying to tell you and did not do it incorrectly. All right. The next thing I want to show you is this. Is that now that we talk about what happened to vector addition and geometrically, what does it mean? The next thing or the last thing I want to talk to you about would be what is a geometrical, okay. What is the geometrical interpretation of a scalar multiplication? Of vectors. So this is basically what it does. So let's say given a vector x in Rn, and let's say given a scalar r, what would happen to when I multiply vector x by r? Well, that depends on several things. Let's say if r is greater than 0, then r times vector x will have the same direction as vector x, but its length is multiplied by r. Okay? And what happens if r is less than 0? So the scalar multiplication basically doesn't change the direction, but simply just make the vector longer. That's basically what it does. However, unless r is negative. So if r is less than 0, meaning r is negative, then r times vector x will have the opposite direction because of the negative involved as vector x, but its length is multiplied by the absolute value of r. Now, some of you might notice what happened to 0. If r equals 0, then r times vector x will just become the 0 vector. So therefore, that's not interesting. Then r times vector x just equal to 0 vector. And that's it. Okay? Important to understand is based on this statement, it's basically telling me that the direction would not change in scalar multiplication, but in scalar multiplication, actually, I should rephrase that. In scalar multiplication, the direction either stays the same or become opposite, but it can change to some other direction. And the length will be multiplied by either r or absolute value of r, which, if you think about it, r itself would be the absolute value of r, because r is positive in the case. So you can generalize in saying that it multiplied by absolute value of r, regardless. And here become, so this is important. So if you take r times vector x and you take the length of it, that just equal to r times absolute value of r times the length of vector x. Now, I do want to just quickly prove this theorem for you, prove this concept for you, and that will be the last thing I want to show you. So this video will be a little longer than 30 minutes, but this should be okay. That way we can conclude 3.2. So here's proof. So what I'm trying to prove is prove this statement. If I take r times vector x, absolute value of that, or length of that, that's the same thing, absolute value of r times the length of x. So how do we do that? So let's go and do this. So once again, just like most of the other property like this, it basically allows me to override the order operation. So the left side of the equation basically tell me I have to multiply the scalar multiplication first and then find the length. And the right side say I can find the length of vector x and then multiply by the scalar. And this statement basically say either way to do it, guess what? You get the same answer, so it doesn't matter. So what I'm going to try to show is show you that. So how? So let's start with the following. So length of r times vector x will just be r times x1, x1, x2, dot, dot, dot to xn. So what I'm going to do is I'm going to just do the scalar multiplication. So that means that's the length of the vector rx1, rx2, dot, dot, dot to rxn. Now I'm going to try to find the length of this vector with rx1, rx2, dot, 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 rxn as the value inside. So based on my formula, that would mean I'm taking the radical of rx1 square plus rx2 square plus dot 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 plus rxn square. Now, based on what we know about real numbers, if I multiply two numbers and square them, technically speaking, it's the same as if I square each number individually and then multiply them together. So it becomes r square x1 square plus r square x2 square plus dot 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 plus r square x sub n square. And now if I look at this sum right here, I notice that they all have a single things that are common between all of them, and that's r square. So what I'm going to do is I'm going to simply factor it out, or essentially using the distributive property to pull out the r square. So become a radical r square times x1 square plus x2 square plus dot 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 plus xn square. And then the next thing is I'm going to use the property of radical to say that if I have two things multiplied inside a radical, I can separate them into two separate radicals. So therefore I'm going to have radical r square and radical x1 square plus x2 square plus dot 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 plus xn square. And guess what? The square root of r square is not r, because square root of r square always generate a positive value. So therefore this becomes absolute value of r. And then the radical x1 squared plus x2 squared plus dot 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 plus xn squared is technically the same thing as the length of vector x. And therefore, this completes the proof. All right, that is the last thing I want to show you in 1.2. So that concludes 1.2. Our next video would be on 1.3. All right, talk to you guys later. Bye-bye.